So we've talked about small rings now and how they can utilize movement and change in their shape to limit their torsional strain. And we also talked about how, because of their fixed positionings, they have the ability to have cis or trans isomers when they are substituted. Now let's move into our bigger ring, cyclohexane. Again, if we looked at cyclohexane and imagined it flat, it would be very strained. Not only is there angle strain, it's at 120-degree angles between the carbons instead of the ideal 109, but every carbon-carbon bond would be eclipsed. So there's also a lot of torsional strain when it's flat like this. The solution here is that the flat conformation of cyclohexane is generally just too high of energy to really be observed, and you don't see this flat version of it. Instead, we have different conformers of cyclohexane. Remember, we're using the word conformer here just to say that this is the same molecule, but different positioning of the same molecule. One conformer is called the half-chair conformer of cyclohexane. So if you imagined the flat ring and you picked up one point of that ring into the air, we'd call this the half-chair. Now, the ring strain here is 10.8 kilocalories per mole, so it's a little bit lower, but you still have a lot of eclipsing going on between carbon-carbon bonds. Another conformer that exists is the boat conformation. We've nicknamed this the boat conformation, in which if you now picked up the other side, so 2 points on opposite sides are picked up from a flat cyclohexane ring. Boat conformation still has a lot of ring strain. It has 7.0 kilocalories per mole of this strain, and it still has some eclipsing of the carbon-carbon bonds. One thing here that is unfavorable is, just like when we talked about our cis and trans, when you pick up the two ends of a cyclohexane ring like this, you have van der Waals strain occurring from these hydrogens that are now closer to each other. The next conformation that's slightly lower in energy is called the twist boat conformation of cyclohexane. It looks a little bit ugly when you look at it here with everything drawn out. This is a kind of more clear and decluttered view of the twist share. So this again has a little bit lower amounts of ring strain. It relieves some of that van der Waals strain because you don't have the two groups coming up as close to each other. They're slightly skewed away. There's minimal angle strain, and there's still some torsional strain. There's still some eclipsed carbon-carbon bonds. The last conformer of cyclohexane is the conformer that is the lowest in energy. The ring strain here is 0 kilocalories per mole, and it is called the chair conformation. We'll be talking a lot about the chair conformation of cyclohexane. The chair conformation achieves bond angles of 109.5 degrees, so its angle strain has been minimized, and it also has minimal torsional strain. So carbon-carbon bonds here are all staggered with no overlap. Because of this, because it has minimized both angle strain and torsional strain in the chair conformation, that makes cyclohexane the lowest in energy. Remember, when we're comparing to cyclopentane. Although cyclopentane has good angle strain, it's minimal angle strain, remember that cyclopentane, even in its different conformations, was not able to minimize torsional strain. So this is why when we looked at that diagram of the heats of combustion, cyclohexane is the more stable molecule. And it's through this chair conformation that it achieves that. Here's another look using this video to look at cyclohexane. You can see that from above, when we start the video, you'll see the flat looking ring. But when you tilt to the side, you can see it in its chair conformation. And this angle right here is the one we were seeing previously here, where you have kind of this up, down, up, down, up, down. Now, another way to view this again is with a Newman projection. And I've shown a still of the video in which when you come down and line up this carbon and this carbon here and here, you can create this kind of double looking Newman projection. Now remember, each of these is a bond going back. And you can see we come down for a carbon on the end point of the ring here. And this one is pointing up here. And these are attached to the carbons that are within the circular Newman projection. So this is how you could draw a Newman projection of a cyclohexane ring. This is an important clue to the stability of the conformation. Remember, I just said that we don't have any torsional strain, but you can actually see it here when we draw the Newman projection. All of the groups are staggered from each other, right? We have all staggered. So how do you draw a chair conformation? We're going to go through this because we'll be drawing cyclohexane a lot and talking about how groups are affected based on the position on the cyclohexane. And this is one of the things that students most often incorrectly draw. And unfortunately, if you draw cyclohexane incorrectly, you don't get some of the finite details of the angle properties that we need to understand when talking about where groups are. So it's very important to talk about these isomers by drawing them correctly. Now, when you use this online software, for example, ChemDraw, which we've gone over, unfortunately, it's just going to give you cyclohexane like this. It's going to give it to you as a flat ring. And we can talk about how to interpret things on a flat ring by using wedges and dashes to show positioning of items. But first, we're going to talk about how to draw it in a way in which you can see all of the items on the ring. So the first thing you want to do to draw a chair conformation of cyclohexane is draw two parallel lines, and you want to slant them either to the right or the left. So as shown below. The next thing you're going to do is add a second set of parallel lines, and they're going to be about at an angle of 120 to the first set. And then the third thing is connect the two fragments. So you're just going to add a connection piece using a third set of parallel lines. Now remember, you can also draw the chair leaning the opposite way. That's if you start with your parallel lines going in the other direction. And these are the same thing. So now let's talk about the positioning of groups on a cyclohexane ring in the chair conformation. If we were to draw all the hydrogens on the carbons on a cyclohexane in the chair conformation, we would divide the positioning of these hydrogens into two groups. Half of the hydrogens we would call pointing straight up and down. These are called axial. They are in an axial position. This is like the axis of the Earth, right? Here is the globe, and I have the axis here spinning around. This is the axial position, up and down. The other half of the hydrogens that are highlighted here in green instead would be called in the equatorial position. These ones are kind of pointing outward. So again, if you looked at your globe, remember that the equator goes around. And so it would be kind of like this area of the globe. If this was a flat piece, the flat area. So equatorial and axial. It's very important to remember the difference between these two. Anything in the axial position are anti to each other. So notice here, if we have an A here, which is in an up axial position, and B on the next carbon over is in a down axial position. These are anti. That's if we drew this in a Newman projection, we looked along the carbon, just like here, they would be anti from each other. And equatorial hydrogens, so hydrogens next to each other in the equatorial positions, are gauche to one another. Remember, that's when they're 60 degrees staggered to each other. So again, if we look along this carbon and we have our equatorial X and our equatorial Y, they would look like this. And these would be gauche to each other. Again, if we looked at a Newman projection of the whole ring and we saw all of our staggered hydrogens, we could color code everything that is equatorial and everything that is axial. And also axial that are up and axial that are down versus equatorial that are up. Now these are just slightly up, or equatorial that are down, which look just slightly down. So again, if this was our ring here, we've shown it in our Newman projection to the side here. Here's our front carbon here. The axial position, which is an up-down position, is very obviously up, and you can see it's highlighted in pink. And all of the hydrogens that are axial up are highlighted in pink as well. Now notice the ones on the bottom of the ring here, highlighted in yellow, they kind of look orange here, are axial down. So they're in a down position, axial position, but facing down. The equatorial ones are a little bit harder to tell the difference between. I'll give you a clue here. If you have a carbon that has an axial that is up, then its equatorial will be down, and vice versa. When you have something that has a axial down, its equatorial will be up. So again, you can see that here. This is the same ring, but just drawn at a different angle. And just as I said, if we have a axial up, I'm going to write AU for axial up, the equatorial hydrogen on that same carbon will be down. And vice versa, if we have an axial that is down, then the equatorial will be up. And you can see these alternate as you go around the ring. We have an axial up, equatorial down, and then an axial down, equatorial up. And you keep doing that going around the ring. So let's try drawing the groups. How do we figure out where groups go if I just have an empty ring? Where do the hydrogens go? How do I know where an axial one is and where an equatorial one is, and if it should point up or down? If you draw your cyclohexane ring properly, as described before, the first thing you want to do is identify a point. Remember, points are carbons. If the point in the ring is pointing up, for example, here or here, it's pointing up in space, you can draw an axial facing the same way. If the point is facing down, its axial goes down. Again, this is up, down. And again, these alternate always. So it's going to go up, down, all the way around. So this is how I would draw my axial hydrogens. I always draw the axials first. I think they're the easier ones to figure out. So next, we draw the equatorial. Now remember, these are going to be slightly slanted down or slightly slanted up. And you can figure out if they're up or down based on the axial. So this axial is up, meaning its equatorial will be slightly down. This axial is down, so its equatorial will be slightly up. And again, we can keep doing that all the way around. This is up, so its equatorial will be slightly down. This one's down, equatorial will be slightly up. And that's how you would draw hydrogens onto a cyclohexane ring. And you can also figure out the positioning of groups, other groups and substituents that go on the cyclohexane ring as well. Now, cyclohexane can flip. It can flip within its chair conformation between two versions. When it flips, everything that was down will be up, and everything that was up will be down. So these rings right here are shown as being the flipped version of each other. If this was position 1, 2, 3, 4, 5, and 6, you would see that position 1 is now up, 2 is down, 3 is now up, and so on and so forth. And if we were to look at where the hydrogens were and position on these rings, what you would see is that everything that was once up becomes down for the carbons, and all the axial groups become equatorial, and all the equatorial groups become axial. However, anything that was an up substituent is still up. So not the carbons themselves, but the substituents. That means the hydrogens or anything attached to it. And everything that was down are still down. So here's a drawing of that, and you can see we have flipped the ring between position 1 and position 2. This substituent, it could be a hydrogen, it could be a methyl group, it could be a chlorine group, is in an axial position, and it is up. It's an axial up. Notice here it has a hydrogen that is equatorial down. This Y group is equatorial up, and it has an axial hydrogen that is axial down. When we flip a ring, remember, everything that is axial becomes equatorial and vice versa. So as each of the positions of the carbons flip either up or down, this X, notice it was on a point going up before, and now it's on a point going down. This X group, you can see, is equatorial now, but it is still up. So it was axial up before, and now it is equatorial up. And it has a hydrogen that was equatorial down, and now that hydrogen is axial down. The Y group, similarly, now is axial. It was equatorial up before, and now it is axial up. And its hydrogen here is equatorial down, whereas it was axial down before. So the main point is that when you have a ring that goes through inversion, so it's the same ring, it just inverts itself, the up and down positioning of a group will still be the same. It will just change between being axial or equatorial. So here's an example. If we put 1-methyl cyclohexane. So I'm going to draw this out in a flat version so you can see it. If we were to draw cyclohexane flat, it would just be a hexagon, right? And we have a CH3 group in the 1 position here. So this is 1, 2, 3, 4, 5, 6. Here we can see that the ring can invert between that methyl being in either an axial position or an equatorial position. Both of the drawings here are the same ring. So these are not different bond positioning of that methyl. They're the same ring. They can be interconverted between each other, so they're just conformers of the same ring. So how do we know when something is a conformational isomer or a constitutional isomer, when they're actually in different positions, or even a stereoisomer? Remember, if something is cis or trans, how do we know? So here's an example. What is the relationship between the two chair conformations below? Now you can see that in the first one, we have two different groups, a methyl group here, and this is an isopropyl group. Notice it has 3 carbons in that Y shape, isopropyl group on a cyclohexane. They're both in an axial position, and if we were to number them, it would look like this. We'd have an isopropyl group here and a methyl group here. So this is position 1, 2, 3, 4, 5, 6. Now these are in the same position on the ring. You can see if this is position 1 and this is position 1, this would be 2, 3, 2, 3. So they're the same distance apart from each other. They're both on a cyclohexane ring. That means that they are not constitutional isomers. We have not changed the positioning of a bond. Now, are they potentially conformational isomers or stereoisomers? Now remember, to be stereoisomers, you have to either be cis or trans isomers. For cis, you have to have your groups pointing the same direction, or trans, it would be pointing opposite direction. So if they were stereoisomers, one would be cis and one would be trans. Now, if we look at these, this is an axial up and this is an axial up. This, however, is an equatorial. And if we look, here is the axial complement to it. So this is an equatorial down. And if this was the axial here, this would also be an equatorial down. So these are both up and these are both down. That means that both of these are cis, right? They're both pointing, in each case, in the same direction, either both up or both down. So we don't have one that's cis and one that's trans, making it so that they are not stereoisomers. These instead are just conformational isomers. They're both pointing in the same direction, either both up or both down. In one, they are just both axial, and the other, they are just both equatorial. So this has just gone through a ring inversion.